Question is the minimum number of logic gates required to implement the following Boolean function. See, if we simplify the following Boolean function, we will represent this Boolean function as AB bar. If we take AB bar as a common, CD bar plus C bar D plus, if we take A bar B as a common, CD bar plus C bar D. So AB bar C exclusive D plus A bar B C exclusive D. If we take C exclusive D as a common, then we will get A exclusive B in the bracket. So we can draw this following Boolean function with one AND gate and two XOR gates. Hence option A is correct. Question is, consider the semiconductor A and B. The figure below shows variation of natural logarithm of resistivity versus 1 by T, where rho is the resistivity and T is the temperature. For the two semiconductors, which is more likely an insulator? See, if we consider two semiconductors A and B, we know that for say conductors it is having a positive temperature coefficient for in case of resistivity. Conductors positive temperature coefficient. So in case of semiconductor B, the variation in the resistivity is higher compared to the variation in resistivity for the semiconductor A. Hence semiconductor B having more negative temperature coefficient, whereas semiconductor B having less negative temperature coefficient. Both are having both negative temperature coefficient, but B is having more negative temperature coefficient. We know that the conductor is having the positive temperature coefficient, means less negative temperature coefficient means it is most likely it is behaving as a conductor, whereas B is having more negative temperature coefficients. Hence B acts as a insulator compared to semiconductor A. Hence option A is correct.
A p-n junction is formed from germanium of conductivity 0.8 ohm inverse centimeter inverse on the p side, 1.6 ohm centimeter inverse on the n side. At 300 degrees Kelvin, Ni equals to 2.1 into 10 power 13 centimeter minus 3 mu h, that is the whole mobility, equals to 2000 centimeter square whole second. Electron mobility is 4000. The relative dielectric constant for germanium is 16. The Boltzmann constant is. Find the barrier potential. Here barrier potential is nothing but I am indicating with V0, which is equals to kT natural logarithm of Na Nd divided by Ni square. Here K is the Boltzmann constant, T is the temperature, is given as 300 degrees Kelvin. Here from the conductivities whatever we have, that is on P side, so Na and D can be determined from sigma P is equals to 0.8, which is equals to Q mu H in A, sigma N 1.6 equals to Q mu electron in D. From these two equations we know Q is the constant, mu H is given, Q is the constant, mu electron is given. So from these two set of equations we can get Na and Nd, and Ni already we have. So if we substitute these values in the equation 1, then we will get V0 as 0.24 volts. Hence option B is correct. A p-n junction is formed from germanium of conductivity 0.8 on p side and 1.6 on n side. At 300 degrees Kelvin, Ni equals to 2.1 into 10 power 13, and the whole mobility is equals to 2000, and electron mobility equals to 4000. The relative dielectric constant for germanium is 16, and the Boltzmann constant K is equals to 1.38 into 10 power minus 16 ergs per Kelvin, and the barrier potential is given as 0.24 volts. Find the depletion width. Here we know the depletion width formula is 2 epsilon built-in potential, that is V0, which is given as 0.24 divided by Q, 1 by Na plus 1 by Nd. Na and Nd we can decide from the conductivities on n side and p side. If we substitute the respective values, we will get 0.19 into 10 power minus 3 centimeters as the answer. Hence option A is correct. The second order active filter known as a Butterworth filter is shown in the figure below. Okay, find out the transfer function of the given network. That means the output by input. We need to find out. See, if we apply here, the potential here is V naught. Here the node potential is suppose VA. If we apply KCL at node VA and node V naught, then we will get two equations. If we solve those two equations, we will get the transfer function for this network as option C